The global aviation industry has depended on one critical technology more than almost anything else: aircraft engines. Passengers may notice the size of an airplane, airlines may focus on route networks, and manufacturers may compete over aerodynamics or cabin comfort. But behind every major leap in aviation history, there has almost always been an engine breakthrough driving it forward. From the first generation of jetliners to today's ultra-efficient long-haul aircraft, engines have quietly shaped the speed, efficiency, reliability, and economics of modern air travel. And now, one engine program is attracting enormous attention across the aerospace world, because many analysts believe it could become one of the most important commercial aviation engines of the modern era, the GE9X engine. At first glance, the GE9X may look like simply another large turbofan engine developed for a new aircraft. But in reality, the story is far bigger than that. The GE9X represents a major technological step forward in efficiency, materials engineering, digital systems, and long-haul aviation economics. And because it powers the next-generation Boeing 777X, the engine is becoming central to the future strategy of modern long-range air travel itself. To understand why the GE9X matters so much, we first need to understand how critical engines are to airline economics. Modern commercial aviation operates on extremely thin profit margins. Airlines spend enormous amounts of money on fuel, maintenance, aircraft leasing, crew operations, airport fees, and logistics. Among these costs, fuel remains one of the largest financial pressures facing airlines worldwide. Even small improvements in fuel efficiency can save carriers millions or even billions of dollars over years of operation. That is why engine manufacturers compete so aggressively. An engine that burns less fuel, reduces maintenance costs, improves reliability, and lowers emissions can completely change how airlines evaluate aircraft purchases. And this is exactly the market environment in which the GE9X was developed. The engine was designed primarily by GE Aerospace as the power plant for Boeing's next-generation 777X program. From the beginning, the goal was ambitious: create the most fuel-efficient commercial aircraft engine ever built for its class, while delivering enormous thrust capability for long-haul operations. And immediately, the aviation world noticed one thing above everything else: the engine's massive size. The GE9X features one of the largest fan diameters ever seen on a commercial aircraft engine. Its front fan alone is so enormous that many aviation observers were shocked the engine could even fit under an aircraft wing. But the reason for this size is rooted in modern turbofan efficiency principles. Modern high-bypass turbofan engines work by moving huge volumes of air efficiently, rather than relying purely on extremely high exhaust velocity. Larger fans allow engines to produce more thrust, while improving fuel efficiency and reducing noise. Over the last several decades, commercial engine design has increasingly moved toward larger fan diameters and higher bypass ratios for exactly this reason. The GE9X takes this philosophy even further. But the engine is not important only because of size. What truly makes it revolutionary is the technology inside it. One of the biggest innovations involves advanced composite materials. The engine uses fourth-generation carbon fiber composite fan blades, allowing the blades to remain extremely strong while reducing weight significantly. Reducing engine weight improves fuel efficiency and overall aircraft performance. The GE9X also uses advanced ceramic matrix composite materials, often called CMCs. These materials are considered one of the most important modern breakthroughs in aerospace engineering because they can withstand extremely high temperatures while remaining lighter than traditional metal components. Why does this matter? Because hotter engines are generally more efficient. Jet engine efficiency improves when engines operate at higher temperatures and pressures. However, traditional materials eventually reach thermal limits under extreme operating conditions. Ceramic matrix composites allow certain engine components to tolerate much higher temperatures, improving efficiency while reducing cooling requirements and weight. This may sound highly technical, but for airlines the result is simple: lower fuel consumption and improved operational economics. And in today's aviation market, efficiency is everything. Environmental pressure is another major reason the GE9X became so important. Governments, regulators, and passengers increasingly expect aviation companies to reduce emissions and improve sustainability. Airlines face growing pressure to modernize fleets with cleaner and quieter aircraft technologies. The GE9X directly targets these concerns. According to industry discussions and company performance goals, the engine aims to reduce fuel burn and emissions significantly compared to previous generation large commercial engines. It is also designed to operate more quietly, helping airports manage increasingly strict noise regulations around the world. But perhaps the most interesting part of the GE9X story is how it fits into the changing future of long-haul aviation. For years, global airlines relied heavily on very large aircraft, like the Airbus A380, to move huge passenger volumes between major international hubs. However, airline economics gradually shifted toward highly efficient twin-engine aircraft capable of long-range operation with lower operating costs. Aircraft like the Boeing 787 Dreamliner and the Airbus A350 accelerated this transition. Airlines increasingly preferred flexibility, fuel efficiency, and lower risk over simply maximizing passenger capacity. The Boeing 777X, and by extension the GE9X, fits directly into this new strategy. The aircraft was designed to offer large passenger capacity while maintaining the efficiency advantages of modern twin-engine operations, and the engine became central to achieving those economics. In many ways, the GE9X is not just powering an airplane, it is powering an entire long-haul aviation philosophy focused on efficiency, flexibility, and sustainability. However, developing such an advanced engine has not been easy. Modern aircraft engines are among the most complicated machines ever built by humans. They operate under incredible thermal stress, intense pressure, and extreme reliability requirements. Even tiny engineering problems can create major delays and certification challenges. The GE9X program experienced exactly these realities. Testing phases revealed engineering challenges that required redesigns, adjustments, and additional validation work. Like many advanced aerospace programs, the engine faced delays connected to durability concerns, certification processes, and integration with the broader Boeing 777X program. And because the 777X itself experienced delays, the engine's timeline became closely connected to the aircraft's certification progress. Still, despite these setbacks, the aviation industry continued viewing the GE9X as critically important because its long-term technological advantages remained highly attractive. Another reason the engine matters is because it demonstrates how aerospace competition is evolving globally. Today's aviation race is no longer only about building bigger airplanes. It is about creating smarter systems. Engines with advanced digital monitoring, predictive maintenance capability, higher efficiency, lower emissions, and greater reliability. Modern engines now contain sophisticated sensors and data systems capable of analyzing operational performance in real time. Airlines increasingly rely on predictive maintenance systems to identify potential problems before failures occur, reducing operational disruption and maintenance costs. The GE9X was designed for this digital aviation era. At the same time, competition between engine manufacturers remains intense. Companies like Rolls-Royce and Pratt & Whitney continue investing heavily in next-generation propulsion systems, sustainable aviation technologies, and future engine architectures. This means the GE9X is not only an engineering product, it is part of a larger battle for leadership in the future of global aerospace technology. And perhaps that is why so many analysts describe the engine as revolutionary, because the GE9X combines several major aviation trends into one platform. Higher efficiency, advanced materials, lower emissions, quieter operation, digital monitoring systems, and next-generation long-haul economics. It represents the direction modern commercial aviation is moving toward. Of course, long-term success will ultimately depend on operational reliability, certification stability, airline confidence, and the success of the Boeing 777X program itself. Airlines care deeply about maintenance performance, durability, spare parts support, and real-world operating economics. But if the GE9X performs as expected, it could become one of the defining commercial aviation engines of the modern era. Because in aviation, revolutionary changes are often not visible to passengers directly. Most travelers may never know the exact engine powering their aircraft. But behind the scenes, those engines quietly determine the future of airline economics, route networks, environmental performance, and global air travel strategy itself. And that is exactly why the GE9X matters so much. It is not simply another jet engine. It is one of the clearest signs of where the future of long-haul aviation is heading. If you enjoyed this deep and research-based aviation documentary, let me know your thoughts in the comments below. Do you think next-generation engines like the GE9X will completely reshape long-haul aviation economics? Or will future breakthroughs come from entirely new propulsion technologies? Don't forget to like the video and subscribe for more high-value aviation content exploring the real strategies shaping the future of aerospace.